Very good afternoon, everybody. My name is Shaik Shafi, Associate Professor, Department of Electronics and Communication Engineering, B.V. Raju Institute of Technology. And today we are going to deal about the course Probability Theory, Stochastic Process. In that, our topic is multiple random variables. So, as you all know, we have already discussed single random variable and behavior of the single random variable. So, how to find the behavior of the random variable? We have gone for distribution function fx of x, which is nothing but in terms of probability x less than or equal to x. So, similarly, if we have two random variables x and y, we need to find the behavior of these two random variables. Similar way, how we found in case of single random variable using distribution function, here also we will use distribution function fx y of x comma y. So, this is what we call joint distribution. This is joint distribution is used to find the behavior of two random variables or more than two random variables. That is what we call multiple random variables. So, mathematically it is defined as probability of x less than or equal to x comma capital Y random variable less than or equal to y. So, if you consider this x less than or equal to x as one event and this as another event, the operation between these two is x less than or equal to x intersection y less than or equal to y. Simply, you can write it as probability A intersection B. So, if anybody asks the distribution function in terms of step function, as we have seen in single random variable case, the behavior of distribution for a random variable x is in the form of staircase. Similarly, here also in joint distribution function, the behavior of the random variable can be given in terms of staircase. That is, the formula for that is summation. As we have two random variables, we are going for two summations. Similarly, probability of x comma y, where x is nothing but from xm, y is from n, and individual step functions u of x minus xm and u of y minus yn. So, here in summation the values are from m equal to 1 to capital M and n equal to 1 to capital N. So, this is with respect to probability, the distribution we can get, and here the function expression is obtained using this second formula. So, as we have discussed already in the first in single random variable case, the properties very important here. Single random variable case properties, what we have discussed, fx of x distribution function, sum of all the probabilities x less than or equal to x is all the time equal to 1. Sum of all the probabilities here. Now, fx of another property minus infinity is probability x less than or equal to minus infinity. There will not be any random variable before minus infinity. So, we will consider it as 0. And fx of infinity, probability x less than or equal to infinity, which is nothing but some complete sample space, which we can consider it as 1. Here, if x is equal to minus infinity, it will be 0. If x is equal to infinity, it will be 1. So, based on these two, we can write it as the distribution function. We have seen already this one in single random variable lies between 0 and 1. So, like this, in case of two random variable, case, the joint distribution fxy of minus infinity comma minus infinity. If the two random variables are minus infinity and infinity, then the value will be probability x less than or equal to minus infinity comma y less than or equal to minus infinity is equal to 1 based on this one individually and this one, and will be equal to 1. So second, if x and y values are both are positive, sorry, here it is 0, here it is 0 based on this one. Based on this one, it will be equal to 0. And fxy of minus if plus infinity, both the random variables are up to plus infinity, then it will be the value of the distribution function will be equal to 1. Suppose if one random variable is negative and another random variable is positive, so that is y, then the value of this one is also equal to 0. Why? Because here probability, if you see the formula, x less than or equal to minus infinity intersection y less than or equal to y. So the intersection, if you consider here, if you consider suppose and 0 intersection sum anything will be equal to 0. Or if in case of minus infinity, if you have plus infinity and x, what happens? fxy of infinity comma y, sorry, this one is y, is fy of y. We will get only y term. Suppose fxy of x comma infinity, we will get the only x term. This is what we call marginal distribution function. These two are marginal distribution function. Similarly, so the minimum value, as if you observe, the maximum value is 1 and the minimum value is 0. Here the joint distribution also lies between the two values 0 and 1. Then the relation between distribution, joint distribution and density, this you can write it in the next case also, but I am giving here itself x comma y in case of two random variable is 2 integral minus infinity to x and minus infinity to y fx y of x comma y dx dy. This is we have seen already in a single random variable case. Then we will move on to another property. If suppose if you want to find the probability between x1 less than x less than or equal to x2 and another event y1 less than y less than or equal to y2. We have seen this formula also in case of single random variable. Here x1, x2 and y1, y2 are two limits. So the answer for this one is fxy of x1 comma y1 plus fxy of x2 comma y2 minus fxy of x1 comma y2 and minus fxy of x2 comma y1. So in case of single random variable, we come across only the two differences, that is fx of x2 minus fx of x1, where x2 is greater than x1. Based on that one, here also we have got this property. So using these properties, we will see one problem that very much important. The problem is like this. You have got two random variables, x and y, and their corresponding probabilities are given as in the table. The random variable x comma y and their corresponding probability is So here the coordinates, the values are 0, 0, 1, 2, 2, 3, and 3, 2. You can take any randomly, you can take. And the corresponding probabilities are 0.2, 0.3, 0.4, 0.1. Check it once whether the sum of all the probabilities are equal to 1 or not. 0.5 and 0.5, which is equal to 1. So now the question is, find distribution function fxy of x comma y. So that is in terms of step function. Step function. Next, find marginal distribution function fx of x and its plot. Then marginal distribution function, another distribution, and its plot. Now, first we will go with fxy of x comma y joint distribution function. As we have seen already in the previous case, so this is the formula we have to use. So we will use this formula. I'll write again summation m equal to 1 to capital M, n equal to 1 to capital N, probability of xm comma yn and individual step functions x minus xm and u of y minus yn. Now we will substitute the values, we will remove the summation, and we have got how many points? 1, 2, 3, 4. So remove this summation and we will find the cumulative addition. The probability, in first case the probability is 0.2, this one. Then u of x will be x and xm is nothing but 0, the first value. Then u of y minus the y1, yn is here 0. Plus the second probability 0.3 and u of x minus 1 and u of y minus 2. Then the third set plus 0.4 u of x minus 2 and u of y minus 3 plus the last one 0.1 u of x minus 3 and u of y minus 2. Hope you are following. Now, this is the expression for the joint distribution function what is mentioned in the question. So the plot of this one is somewhat difficult, not I would say, because we have x term, y term and distribution. So in exam also you will not be asked the plot of the joint distribution function. However, the plot of marginal density functions. Why? Because you are plotting graph between one random variable and its corresponding marginal distribution. Whereas in this case, you have got 3 terms total, x, y and joint distribution. So in examination, you will be asked to plot the behavior of random variable marginal distribution function only. So the coming to the marginal distribution function formula, fx of x as already mentioned, summation m equal to 1 to capital M and the probability, there will not be any change in the probability, joint probability will be as it is, xm comma yn, but the step function will be x minus xm only, they will not be having y minus yn as per the property. Now, corresponding probabilities, if you see here 0.2, 0.3, 0.4, 0.1 and we need to consider only x random variable only 0, 1, 2, 3, 0, 1, 2, 3. So here I am substituting those values 0.2 2 into u of x minus 0 plus 0.3 u of x minus 1 plus 0.4 u of x minus 2 plus 0.1 u of x minus 3. So once you check it, the values are only x 0, 1, 2, 3 and the corresponding probability is 0.2, 0.3, 0.4 and 0.1. So these are correct. Now fx of x, this is the expression for marginal distribution function. Now coming to the plot, y-axis represents distribution, marginal distribution, and x-axis represents the random variable. The values of the random variable are 0, ranges from 0, 1, 2, 3. This is given already in the table. Now you please mark the values distribution function, that is first 0.2 and then 0.2 plus 0.3, 0.5, 0.5 plus 0.4. This is probability x less than or equal x means up to that point you have to consider. Cumulative addition of that one is what we call distribution function, that we have already studied in single random variable case. Same thing you need to apply here. 0.5 plus 0.4 and here 0.5 plus 0.4 is 0.9 and the last one, the highest value in case of distribution is 1. So at 0 the distribution is at 0.2 and it will be dragged up to 1. It will be continued up to, distributed up to the random variable x equal to 1. Then at x equal to 1, the value is 0.5. The distribution, marginal distribution value is 0.5 and it will be continued, distributed up to the 0.2. Then for 0.2, the value is 0.9. And it similarly it is continued up to 0.3 and at 0.3 the maximum value is 1. So this is the marginal distribution curve which gives the distribution of x or behavior of the random variable x individually when joint probabilities are given and joint distribution is also mentioned. From that only we have got marginal distribution function. So the individual step size here is nothing but here it is 0.1, the difference of these two is 0.4, the difference of these two is 0.3, difference of this one is 0.2. Individual step size gives the probabilities, corresponding probabilities. This is also clearly explained in while discussing single random variable case. Now we will move on to the second marginal distribution function fy of y. We will write according to this one, summation n equal to 1 to capital N, the joint probability will be same. There will not be any change in the joint probability, but you will be having only one stair, that is step function u of y minus yn. Now similarly what we have done in case of single random variable, we will continue the same procedure in obtaining the marginal distribution in case of another random variable, that is y. So here if you see the values are 0, 2, 3, 2 and the corresponding, there will not be any change in the 0, 2, 3, 2. So the values are 0, 3, 2 and 2. 2, 3, 2. These are the values. Now using this one, we will write the probabilities are common, 0.2 into u of, now y will be coming minus 0 plus 0.3 u of y minus 2 plus 0.4 u of y minus 3 plus 0.1 u of y minus 2. Now if you observe, you have got here two step functions with the same value, same expression, u of y minus 2 and u of y minus 2. You add these two and the resultant one is 0.2 u of y as it is 0 plus add these to 0.4 u of y minus 2 plus 0.4 u of y minus 3. Now even if you add all these things, again probability is equal to 1. So now plot of this one is, if you observe, y-axis is the marginal distribution function fy of y, and the x-axis is the random variable y, and the values are from 0, 1, 2, 3. So of course we have got random variables 0, 2 is repeated here, 3, then again 2. So maximum value is 3. Even if you skip here 1, doesn't matter. 0, 2, 3, for that you will be plotting. For understanding purpose, I have taken 0, 1, 2, 3 values. Now mark the distribution values, cumulative values, 0.2, and then addition of 0.2 and 0.4 is 0.6, and addition of this one 0.6 to 0.4 is equal to 1. Now at y equal to 0, the distribution function is 0.2, and it will be continued up to y equal to 2. As we don't have this one, and it will be distributed up to 2. At 2, the value is 0.6, and it is distributed up to y equal to 3, and at 3 the maximum value is 1. So here also the individual size of the steps is nothing but the probability, corresponding probability, 0.2, 0.4, and finally again 0.4 you are getting here. So this is how you have to calculate the joint distribution function if two random variables are given, and marginal distribution functions fx of x and fy of y, and their corresponding plots using the formula probabilities. This is what all about joint distribution function. Similarly, we have got what we have seen, x and y belongs to the category discrete random variables. We have gone for behavior to obtain using distribution function, joint distribution function. If x and y belongs to continuous random variables, then the behavior is obtained using joint density function. We have already seen this one for single random variable joint density, density function. Now we will apply the same concept, density function, for two random variables which are of the type continuous. So we have got here fxy of x comma y is derived from distribution function, the formula defined as dou square by dou x dou y distribution function fxy of x comma y. This is obtained. We have seen density function fx of x is the differentiation of the distribution, single random variable. Here the two random variable case. Similarly, the distribution, the density function is integral minus infinity to x and integral minus infinity to y, small fxy of x comma y dx dy. So we have seen the distribution function in terms of step function. Already we have seen probability of xm comma yn u of x minus xm u of y minus yn. So what would be the expression for the density function? That is equal to, we have seen differentiation of the distribution function. Here in this case we will get delta of x minus xm and delta of y minus yn, and there will not be any change in the probability. Derivative of the step function gives an impulse. So this is the expression for, and no change in the summation. This is the expression for joint density function. Then coming to the properties. Integral minus infinity to infinity, the joint density function over an area minus infinity to infinity, fxy of x comma y dx dy is equal to 1, satisfying the valid joint density function. And fxy of x comma y value is always non-negative, that means greater than 0. Now next, as per single random variable, we have seen this property also, probability in case of single random, x1 less than x less than or equal to x2. In single random variable case, we have seen integral x1 to x2 over limits fx of x dx. Similarly, for two random variables, x1 less than capital X less than or equal to x2 comma y1 less than y less than or equal to y2. Here it is integral two limits x1 to x2 and y1 to y2 fx y of joint density function dx dy. Now here also we will come across the marginal density functions. Fx of x equal to integral minus infinity to infinity fxy of x comma y dy, and fy of y equal to over minus infinity to infinity fxy of x comma y dx. These two are derived from joint distribution functions fx y of x comma y and its marginal distribution functions. These two are derived from these two. So remember, the marginal density functions are fx of x equal to this one, fy of y equal to this one. Now, how a problem will be asked in terms of, if x and y are two continuous random variables, you can expect find marginal density function fx of x and fy of y, and you will be given the joint density function, however, fx comma y. Now we will see one problem related to joint density function as well as marginal density function. Suppose given fxy, if x and y are two continuous random variables, x and y are two continuous random variables, then the density function, joint density function is given by 1 by 18 e to the power of minus x by 6 plus y by 3, and this is for x greater than or equal to 0 and y greater than or equal to 0. The question is find marginal density function. Straight away find fx of x and fy of y using the joint density function. Individually you are finding. See here, joint density function given for two random variables, asking the density function for the individual one. That is what we call marginal density functions. So now we will find, we have already seen fx of x equal to integral minus infinity to infinity fxy of x comma y dy. Now substitute the values. Now the function is for x greater than or equal to y greater than or equal to 0. That means the limits are not from minus infinity to infinity, but you have to change 0 to infinity. So now we will substitute 0 to infinity, and the value 1 by 18 e power minus x by 6 plus y by 3 dy. Now with respect to y, x term is constant. Now you can take this one and this one. 1 by 18 e to the power of minus x by 6 integral 0 to infinity e power minus y by 3 dy. Now 1 by 18 e to the power of minus x by 6, the value of this one, e to the power of integration e power minus y by 3 by minus 1 by 3 over 0 to infinity. And this will be 1 by 18 e to the power of minus x by 6. So upper limit, if you substitute, the value is 0, e to the power of minus infinity is 0, and minus into minus plus, the lower limit, e to the power of 0 is 1 by 3, then this is equal to 3. Then finally, the marginal density function fx of x is e to the power of 3 by 18 e to the power of minus x by 6. That you can write it as 1 by 6 e to the power of minus x by 6. The answer is in terms of x. This is for x greater than or equal to 0. Similarly, you can find out the marginal density function fy of y is equal to integral minus infinity to infinity, writing the formula fxy of x comma y dx. Now here limits are again from 0 to infinity, 0 to infinity. The value is 1 by 18 e to the power of minus x by 6 plus y by 3 into dx. Now on solving, you will get similarly what we did in the earlier case. You will get 1 by 3 e power minus y by 3 for y greater than or equal to 0. So marginal density function fy of y, and the answer is also in terms of y. So this is the way we have to find the behavior of the random variable x and y, multiple random variables. If it is of the type discrete, we have to go for joint distribution and marginal distribution function. And if x and y belongs to continuous random variable, then we have to go for, to find the behavior of such kind of random variables, density functions, joint density functions, marginal density and marginal in terms of x as well as y will give the behavior of the random variable. How the random variables are spread can be obtained using distribution, joint distribution and marginal distribution, joint density and marginal density function. So next class we will see the statistical independence of random variables. That is nothing but distribution as well as again density functions. That we will see in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.